Thanks, Adam, for putting it together. Thanks for all the organization and for doing the slides also. Of course, thanks for having me. So I'm going to be talking about benchmarking protocols for evaluating small parts robotic assembly systems. It's kind of a long name for benchmarking assembly systems, essentially. So a little bit about me. You can say next slide. Go next slide. Yeah. Right out of college, I came to NIST, National Institute of Standards and Technology, as a mechanical engineer. And since the beginning, I've been doing robot testing. Previously, my work was in response robot related work. So like a bomb squad's bomb disposal robot, or maybe a soldier out in the field might have a throwable disposable robot. Those are the kinds of test robots we worked with. And then more recently, I transitioned over to this other project for about 2 years, where I worked with assembly robotics. And that's where most of my work has been focused on the assembly task boards. Other work includes like grasping or reliability of motion of a robotic, like industrial arm use. Next slide. A little bit of a background about why we do what we do, why the task boards. And the problem is that there's this gap. Technology is out there that can do specific assembly tasks, automation and robotic specific tasks. But the problem is that the companies, the SME or small, medium-sized enterprises, aren't necessarily adopting these technologies. And they're still using a highly trained engineer to come in for a week to program the robot to do the task. And as we know, that's time and money to have to reprogram it. And we know that it's possible to do better. So we're trying to push the technology and more specifically benchmark their performance. So the assembly-based robotic tasks hopefully will push the design and solve the problems associated with low volume, high mixture manufacturing. That is, say somebody wants a part, but they're going to build something 5,000 units, and then they're going to change it, and they're going to have to reprogram to do the next 5,000 units of something else. That's becoming more and more common in the industry, and so we're trying to get away from this expert on the field for a week trying to reprogram the robot. The task boards specifically are designed for assembly-based robotic tasks. The most common one might be peg and hole insertion, or maybe bin picking, but then kind of evolving from there. They benchmark the basic tasks in task board 1, and then ideally in task board 2 and 3, and then maybe for whatever foreseeable future, the goal is to benchmark their performance against belt drives, for example. That's a common issue, a common assembly problem. Or maybe handling wires, wire harness, or cable routing, loose parts, maybe dual hand manipulation. We're trying to solve all these problems by presenting the real world problems out there on the task board and benchmarking what they can and can't do. Next slide. So here are the task boards so far. Task board 1 you all might be familiar with, or at least most of you. This one deals with the basics. It has 4 round pegs of varying sizes, 4 square pegs of varying sizes. Those are all peg and hole insertions. And then it has common connector types, USB, Ethernet, and then 2 other types. The name escapes me right now. Different sizes, different orientations, and then threading nuts on different size bolts, and then gear meshing. And that kind of transitions, I think, rather nicely over to task board 2, which is belt drives. Originally, the idea came from a competition, which I'll talk a little bit more about later. But it also is a very common assembly robotics issue in industry, belt drives of all kinds, shapes and sizes, which is why the board kind of spans the gamut. The first one being a chain and sprocket kind of drive, over to a round belt, and then over to a timing belt. A timing belt you might see more in automotive. The 3 tensioners that are involved in the belt drive units are vastly different from one another, again, to try to span the capabilities and to show different capabilities if you can do one but not quite the other. you have a more specific understanding of what your robot can do. And then lastly, the cable routing, and that is mostly to deal with flexible parts. We have 3 cables, one thin audio 3.5 millimeter jack cable, an Ethernet, much stiffer to work with cable, and then a SATA cable, something you might see in your computer, in the guts of your computer. The idea is that it's a flat cable, and so you have to manipulate it a little bit differently than the other 2. Next slide. So for each of these task boards, we kind of designed a protocol, or a way to use these task boards so that you actually can quantify how well you've done or what you can and can't do, and then maybe for your comparative purposes, you challenge the next guy, see what he can do, or challenge yourself against your own time, and then push the technology and ideally be able to do the task board a little bit better the next time. Each one of them is going to be done essentially the same way, starting with a disassembly. So you would start with the board assembled with a kit tray next to it. And the idea is just take the thing apart, take all the parts out, put them in the tray. Pretty simple. Secondly, you would have to reassemble the task board. Much more points associated with the assembly, since that's typically what we're aiming for, what the capability we're aiming for is. But also because there's a lot more discretized possibility here. You can insert a USB, but then you can also fully seat the USB, as an example. You can start to put the peg in a little sideways, or you can fully seat the peg through the board. So you can imagine there's partial points for partially completing the task board, which again helps benchmark specifically what you can and can't do. Next slide. So we'll kind of go through the task boards. Task board 1, the examples on the right side show first some incomplete partial points, maybe 1 or 2 points for the first part. And then the highlighted in green shows a completed task. Top right one is a BNC cable, and then the peg, and then the gear, which is both seated and meshed with the gear next to it. And this just shows kind of the 4 cylinders, what the size are, and then kind of the partial points or how you would receive full points. I'll give that a second. And next slide. This is belt drive or task board 2. Partial points for this one might be for threading one pulley but not quite the other, and then threading the opposite one, points for each pulley, and then lastly tensioning the belt. The example on the right is just the round belt, but you can imagine the chain belt and the timing belt work very similarly, getting it around the first 2 pulleys and then tensioning it. The tensioners are different, so maybe the points for each tensioner would be different. But the idea is that each task has a point associated with it. And I'll give this a second just to look through, see what the tasks are. And next slide. Lastly, cable routing. Unfortunately, I didn't have any good pictures of partial points for this one, so I just took pictures of each of the cables. Ideally, a partial point for maybe the first section would be to go around the pegs in the top right, but not quite in the right orientation. Right? We want to have you route cable around pegs, around things, accurately place the cable, and thread it through things. So let's say you accurately place the cable, but it's in the wrong direction. You won't receive the points for that. It's important that you understand your problem and are able to solve it correctly. So the correct orientation and direction is important, and then also the task itself, actually threading it around the peg as opposed to missing that peg, for example. And then lastly, at the end of the task, getting your wire all the way through is rewarded with the task board 1 type task, and that is to just seat the connector in the female connector at the other end. Okay, next slide. So some design reasoning why we chose what we did. I said already that we want to associate the tasks with the problems in the real world, but also we got a lot of our numbers from a book by Boothroyd and Dewhurst, Product Design for Manufacturing and Assembly. where they quote specific times, handling times, for example, insertion, routing, just how long does it take a average worker to do a task, down to specifically with their fingers picking up the tool, which could only take a half a second. And they have charts in there that allow us to compare how long it might take a person to do each task on the task board individually. And those might be some good benchmark goals for a robot arm. If you were trying to get within human time or better, then you'd have those values at least roughly to compare against. I can say personally that after having done the task board, that the numbers in these charts are pretty close. Obviously, there's a lot of variation. People go different speeds. Whether or not you know it's competitive or not will make you go faster or slower. But they're pretty reasonable to the handling. You know, they're not off by tens of seconds. So that's food for thought if you ever wanted to aim for those numbers. Next slide. And then, like I was saying, let's talk about competitions. Back in 2017, there was a competition where it was mostly bin picking and kitting and placing things in certain parts. I wasn't able to attend this one. Joe Falco did attend, and it kind of used the task from Task Board 1. And then onto WRS in 2018, they kind of asked us to build a belt drive type task board so that they could use that to, to quantify, well, why did they choose the task that they did, and this kind of helps them reference, standard data, ideally, not necessarily data, but standard reference materials or standard apparatus that they can use for their challenge. And then conversely, we used their layout to kind of motivate our design as well as a very dual effort. And most recently in 2019, IROS 2019, we kind of brought the task boards together, and we brought at least one aspect from each of the task boards and then added some screw threading in there, and then had teams kind of do the whole thing. We want to know what they're capable of, what kind of technologies are out there. So they brought the best that they could offer, and then did as much as they could within a certain time. That was a pretty exciting challenge. It was exciting to see what they can and can't do. Future goal is in IROS 2020 to maybe, given the whole Corona thing, have a virtual competition where teams might submit a video of them doing the task, and then we'd be judging after the fact, just as a goal or an idea. Next slide. So you guys hopefully have some solutions of your own. We've seen a few of them where we are excited to see what kinds of things you come out with next. Previously, and unfortunately, even at this competition, teams are still showing up with lead-through programming, which certainly has its benefits. It's very user-friendly. They're doing the drag app for programming, where they might just go here, and memorize that series of code. The problem with that is if the task board shifts at all, or if anything changes, you have to reprogram the entire robot. So we want to push the technology for more innovative solutions, maybe using CAD data or force feedback sensors or vision processing. We have seen a little bit of that. We'd love to see more of that. So hopefully today we get to talk about kind of your guys' solutions, having worked on the task board 1, or maybe your goals if you do get task board 1, how you might solve those issues. Next slide. So just in closing, benchmarking robot system performance on assembly task boards by NIST hopes to encourage progress in the field, as well as assess future robot system capabilities for choosing the best system for the intended application. We are always welcome to feedback about the designs, issues that you come up with. Maybe it doesn't quite represent the real world the way you'd like it to. Maybe it's a little bit too difficult. Now we kind of want it to be difficult. We do want to push the technology. challenge people to find better solutions. But maybe you have an idea for a new task board. We are very welcome and open to ideas. And thank you for your time. Hope I didn't go over. I don't know what time it is.
I actually turned off my my timer because you were right on time. I figured might as well not interrupt your closing statement.
Yeah, I practiced a few times before. I know I was going a little fast, but that's because I knew I would go long. I do have some slides of just the task boards if anybody has any questions specific to them. Those are the following slides. Yeah.
All right. So thank you, Kenny. Let me bring these down. See if we have any questions in our chat. All right, so question from Cindy. What about 3D non-planar? Cindy, do you want to maybe add some detail to that question?
Yeah, I mean, like I went to Boeing's airplane assembly thing, and I'm gonna put my video up if I can. So one of the things that I saw them doing there is they had this like pilot console, and so they had these pieces to put together, and like they had to do bolt, 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 right? So there was definitely a lot of this moving around a shape. So what about extending these? Are you thinking about extending these boards at some point to something that's 3D so that you actually have to deal with actually moving the arm around to do the same assemblies?
Yeah, currently each of the task boards has in the four corners these screw holes for mounting. We encourage teams to mount it on a wall vertically, for example, or upside down, solve the problem in a different way. Recognize that it's only 2D in its own field, right, relative to itself. But you saw the competition, one of the competitions used the belt drives, and that one was, you kind of had to be on either side to put the parts together on a vertical belt drive. It's an interesting idea. I think that maybe future designs could encourage that, but for now it's just placing your board on whatever surface you might want. Any other questions?
So in that context of using them three-dimensionally, has that actually been exercised at any of the competitions yet, aside from the belt drive? And maybe a kind of follow on to that is, what do you think maybe is holding people back from doing maybe more complex activities like that, as opposed to just using it flat planar?
Well, I think it's a stepwise approach, right? So they want to know with confidence that they can do the task board in its easiest variants first. Task board 1 is relatively simple. A lot of people can do that one all the way through. I would encourage them start expanding. I imagine that part of their issues, and I don't know, I'm not an expert in the field, but I imagine some of their issues is the vision processing. Being able to see something 2D is a lot easier than the shadows associated with something vertical, or being able to get the right camera angle to associate the Z depth of one object over another, if they were using that. Force feedback can be another issue just because of the physical limitations of the robot. If you're pushing against a surface, you want to be as perpendicular to it as possible, but it might be difficult if there's something vertical and your arm is all contorted to try to push horizontally against it. But again, I'm not an expert. So I don't know, maybe you guys can tell me.
Hi, this is Joe. Can you guys hear me okay?
Yes.
So one thing we might incorporate in the future is similar to what Japan did during the World Robot Summit. As Kenny mentioned, there was a NIST a task board type design that followed the NIST methodology for task boards, but they also had the same components that were on the task board were actually assembled into a complete assembly. So this would be more realistic to what you would find in the real world. So while we just took a first step into assembly using task boards, as more and more people adopt the use of the task boards and are pursuing these types of this type of research, then of course the next progression would be to try to put together assemblies that have the same components that were on the task board. And that requires a more integrated system. Typically you would need more dual arm manipulation to enable you to accomplish such complex assemblies.
Yeah.
Did you say that any of that was planned for World Robot Summit, or that just might be the venue where it would get used?
Well, that's in World Robot Summit in 2018 is where they did that, and will whenever 2020 competition occurs, they'll do the same thing. So maybe it will be time in the near future for NIST to incorporate such assemblies to the actual components on our task boards.
Sure.
Anybody else have a question they would like to ask Kenny? All right, do you want to say anything about the resources on the screen here?
For interest of time, thank you everybody. So actually specifically to NERV, who is passing out these task boards. Yeah, and oh, we have a website if you're interested in looking at the task boards and downloading them. They're all, you can download them. They have the CAD parts associated with them if that's interest to you. And then the links for NERV, or if you are interested in getting the task board for yourself. At least I hope they still work, those links.
They do, yes.
Okay, yeah.
And they're, at the end of this workshop, there will be an opportunity for attendees to potentially receive a task board for free. So stay tuned to the rest of the workshop to learn more about that. That's how you keep people in,
That's right.
That's right. Okay, Kenny, thank you very much.
Thank you.